Okay, hello everybody. I know you guys have been listening to Mr. Rutherford for a few days, so it's my turn. This is Mrs. Hilvert, and today we're going to go through the binomial theorem and Pascal's triangle and just kind of show you some cool number patterns that develop. So your homework is just going to be 1 through 25 odd, the practice problems for this, and we'll have the keys posted. So to start, if we asked you to expand this, it would be pretty easy. We would just FOIL and get x squared plus 6x plus 9. But what if we then said, okay, do 3x minus 5y to the 10th? Yikes, right? If we had to FOIL this out and then multiply by this and keep going, it would take so long and the numbers would be so big, and it would probably take a couple pieces of paper and leave a lot of room for error. So in comes the Pascal's triangle. In your book, it's interesting because it says that it wasn't actually discovered by Pascal. He just got the name for it because he was one that used it. And it appeared in 1303 in a Chinese text called The Precious Mirror, who referred to it even then as a diagram of the old method for finding eighth and lower powers. So it honestly works for eighth and higher powers too. And it's just a pattern of numbers. If you look, so all the first and last numbers are going to be ones. We'll just do a couple so you can see the pattern. And then the next numbers are a sum of the numbers above. So it's 4. And actually, it's the different ways that you can get to this shape on the graph. So like you can only get to this one way going this way. But to get to this one, you could go one way here, this way. You can go 4 different ways. It would take you 6. You could go 6 different ways to get here, 4 to here, 1 to here. So the next row, 1 and 4 would be 5, 6 and 4 would be 10, 1 and 4 would be 5. The next row, 5 and 1 would be 6. This would be 15, 20, 15 and 6, and so on. So that's how you find the numbers in Pascal's triangle, and then you use them for the coefficients of your binomial expansions. Now on the next page, I don't want you to get too intimidated by this formula. I personally just find it easier to show a couple examples, but before that I am going to write out a couple of tips. So first things I want you to notice is that the powers of A decrease. So the first term in the binomial, n minus 1, it would be n minus 2, n minus 3, and so on. And then your powers of B increase. And so you can see here that there is none. That would be B to the 0, B to the 1, B to the 2, all the way up to B to the n. The other thing maybe just to keep in mind is that you're always going to have one more term than the power. So in other words, for this example, if we're going to expand this using Pascal's triangle, we're going to have 6 terms, okay, because this is something to the 5th. So if you want to flip back, you can. I'll go to mine, one of these that I have here. Yeah, yikes, if you were doing that, right? If you go to the 5th row, you can see it's 1, 5, 10, 10, 5, 1. So those are going to be the coefficients that we start with for that row. And so our A is just A and our B is B. That will change throughout, but in this one we're just using A and B. So we have a 1, and we're going to start with A to the 5th and B to the 0. Something else to note is that the sum of the exponents is always going to be the power. So like our next term, we're going to have 5, and then we're going to go down A to the 4th. We're going to increase B to the 1st. 4 plus 1 is 5. Our next term is going to be a 10, and now we're going to be at A to the 3rd and B squared. And again, 3 plus 2 is 5. Another 10, we're going to go A squared, B to the 3rd, 5, b to the 4th, and then finally 1, b to the 5th. So again, let's point out those patterns. We have the coefficients 1, 5, 10, 10, 5, 1. And then we start with a to the 5th, a to the 5th, a to the 4th, a to the 3rd, a squared, a to the 1st, a to the 0. And our b goes the other way. B to the 0, b to the 1st, b squared, b to the 3rd, b to the 4th, b to the 5th. The final thing to note, all of the exponents add up to 5. This would be a 1 and 4, and a 0 and 5. Okay, so let's try another one. X plus y to the 7th. So if you turn your paper over, sorry, I keep getting crooked, and look at the 7th row, the coefficients for the 7th row are 1, 7, 21, 35, 35, 21, 7, and 1. So we're going to start with x to the 7th, and it would be y to the 0, which you don't have to include if you don't want. So we would probably more in a standard way see this as x to the 7th, because y to the 0 is just 1 times 1 is 1. So then I'm going to have 7x to the 6th y plus 21x to the 5th y squared. Some people like to go through and maybe just put in all the x's. X to the 3rd, x squared, x, and we wouldn't have one for that. And then go in and put in the y's. So y to the 0, y to the 1st, y squared, y to the 3rd, and leave myself enough room there, y to the 4th, y to the 5th, y to the 6th, and y to the 7th. And that's your expansion if you were to work out x plus y to the 7th. See, way easier than actually doing it by hand, right? Okay, the last two examples for this get a little different. You can see here that now we don't just have a variable. We don't just have an a and a b or an x and a y. We have a coefficient on x, we have a square on y, and we have a negative. So this is going to involve a little bit more. So first off, since we're in the 4th power, we're going to go to the 4th row. And our coefficients for that are 1, 4, 6, 4, 1. Then I'm going to write up here what my a and b are. My a is 2x, and my b is going to be a negative y squared. Okay, so we're going to start with our 2x to the 4th. This is going to be 2x to the 3rd, 2x squared, 2x to the 1st, and 2x to the 0. I'm just going to show you a different way to organize your information. You can do it however you choose. Now I'm going to go through and do my negative y squareds. So negative y squared to the 0, negative y squared to the 1st, negative y squared to the 2nd, negative y squared to the 3rd, and negative y squared to the 4th. Okay, now I have to simplify all of this. I check all of my exponents add to 4, so I'm good. But now I need to get this simplified. So on my first one, 2x to the 4th, remember, is 2 to the 4th and x to the 4th. 2 to the 4th is 16. This is 16x to the 4th. Anything to the 0 power is 1, so that's not going to have an effect on my answer. So this first term is just going to be 16x to the 4th. My next term, this is going to work out to be 8x to the 3rd times negative y squared, because I'm doing to the 1st power. I can't forget about the original coefficient of 4. So I have 4 times 8 is 32. times negative 1. So minus 32 x to the third y squared. Next, 2x squared is going to be 4x squared. Negative y squared squared. This is like a negative 1. Well, negative 1 squared is a positive 1, and this is going to be y to the fourth. So I now have to do 6 times 4, which is 24, times 1, and then x squared y to the fourth. Okay, next, we don't have to do anything here. Negative 1 to the third power is still going to be negative, and this is going to be y to the sixth. So I have 4 times 2 is 8, times negative 1 is negative 8. I have x to the power of 1 and y to the sixth. And finally, 2x to the 0 is just going to equal 1. Negative 1 to the fourth is just going to be a positive 1, so a y to the 8th then. 2 times 4 is 8. 1 times y to the 8th is going to be y to the 8th. You're going to notice when you're doing these that your positive and negatives are going to alternate, so that's good. I also see some other patterns in here. Even though now my final answer isn't going to be where my exponents add up to 4 because I had that y squared, note that it goes 4, 5, 6, 7, and 8. So there's all kinds of patterns to look for. Okay, another type of question that's pretty common to see is to ask for the coefficient of a specific term in an expansion. And there's a little bit of back work that we want to do to show you a pattern that you can use to get this started. So I'm going to go back for a minute and just think about if I had x plus y to the fourth. If you look at your Pascal's triangle again, you'll see that your coefficients are 1, 4, 6, 4, and 1. And remember, I would have x to the fourth, x to the third, x squared, x to the first, x to the 0, and y to the 0, y to the first, y squared, y to the third, y to the fourth. Okay, the pattern I want you to see is this first coefficient, the number from the Pascal's triangle. I'm in the fourth row. 1 is the same as 4, choose 0. You can put it in your calculator if you want to see. 4 is 4, choose 1. 6 is 4, choose 2. And so forth. If you notice, this is the same. So 0 and 0, 1 and 1, 2 and 2. Okay. Okay. So if I want to, let's go back to our problem now. So if I want to find the coefficient of x to the 10th term in this expansion, I know that I'm going to have, it's going to be x to the 10th and 2 to the 5th. Because it's the first term, it's the x to the 10th, and they have to add up to 15, and the y is my 2. Now, as far as the coefficient goes in the Pascal's triangle, I'm going to have 15 choose 5. Because remember the pattern that I discovered. It was the exponent, so 4 in this case, right? Choose the exponent of the second term of the b. Again, it was 4, choose the exponent of the b, or the second term. So in this problem, I'm doing 15, choose 5, because that's the exponent of my second term. So when I plug in 15, choose 5, I get 3003, and 2 to the 5th is 32. So then I have to do 3003 times 32, and I get 96,096. That would be the coefficient of my x to the 10th term. Okay, there you go.